This is a story of two car body panels. The panels were made from two lots of steel. Both lots passed inspection for surface roughness, but when the panels were painted, one looked great and the other did not. So, what was different if the average roughness was the same? The answer is in the spatial wavelengths. Surface texture consists of a spectrum of spatial wavelengths. We set cutoff wavelengths to define roughness and waviness based on the application. When the inspectors measured the steel, they used standard cutoffs per the drawing, and with those cutoffs, the average roughnesses were within tolerance. The trouble was, the real problem was over here, outside of the measurement range. These 3D measurements show the surfaces of both lots of steel, with the cutoffs that the inspectors used. These are the surfaces we think we are painting, and if these were the surfaces, we'd get the same finish for both. But here are the surfaces with the full spectrum of wavelengths, what we are actually painting. When we consider the full spectrum, the differences in the steel lead to much different finishes. Because of the cutoff wavelength we used, this important difference fell outside of our roughness range, and, since we only inspected roughness, we missed it. By shifting the cutoffs to measure across the wavelength spectrum, we can see the ranges where the biggest differences occur and catch potential issues. Software like Digital Metrology's Bandify 3D does this automatically. By analyzing the wavelengths that matter in our application, we can find differences that we might otherwise miss and take steps to control them. And that's the key to a smooth finish.